Thank you for joining the Red Team Village at HacktivityCon today. Our next speakers are Dimitri and Giorgio, and their talk is about PEzoNG, which is an advanced packer and automated evasion on Windows. Don't forget to join us in our channel on the HackerOne Discord server.
Welcome everybody, and thank you for taking your time to attend our talk about PEzoNG, an advanced packer for automated evasion on Windows. My name is Giorgio Bernardinetti, and I am a cybersecurity researcher at CNIT in Italy. My work involves mainly penetration testing, malware development, and training.
Hi everyone, I am Dimitri. I am a security consultant and researcher at SecForce, and my research is mostly focused on red teaming, and in particular on malware development and OS internals. So we will start with a brief introduction to give you some concepts about packers, and then we will dig into PEzoNG architecture, and we will start digging deeper and deeper, showing you all the important aspects of how our packer works, and giving you also some insights about Windows internals and showing you why this works. So let's start. Packers. Packers are software that are used to embed code into other binaries. So in Windows, we can embed like exe, DLLs, or even shellcode into another binary, hiding basically what is like the real binary. And this is used also by software houses, so packing is also used for legit purposes, because it helps to protect the software from reverse engineers. And in our case, we want to use packers because we want to bypass antiviruses, and so the objective of PEzoNG is to get AV safe binaries. To achieve our goal, we will have to address both static and dynamic analysis, and, moreover, we will need to compile it in a way that should avoid trivial signature-based detection. To hide the malicious payload, we will use encryption. However, the payload loader can't be encrypted, and, for this reason, we will need a way to make the payload loader polymorphic, so that we will have a different binary at each compilation, and, in this way, signature-based detection won't be effective. Let's dig into the PEzoNG architecture. So we were inspired by the idea of PEzoNG, which is an open source packer developed by Fra. PEzoNG has a modular design, and it allows to customize a lot of features. For example, we can choose between different unhooking techniques or between different memory allocation schemes, and it is very easy to add new techniques or new memory allocation schemes or new encryption algorithms, because the design allows to just add the code, and with minimal change we can implement the new feature and use it inside PEzoNG. Another important feature is that we have polymorphic output binaries, which means that static analysis and signature-based detection won't be effective, and we will talk more about this later on. Finally, there is a web GUI that allows the user to choose the setting in an easy way. Let's dig into the packing process. We start encrypting the payload and we embed it into a C++ template, then we compile everything to get LLVM intermediate representation, we obfuscate the intermediate representation, and then we link all the object files to get the final binary. The unpacking process is slightly more articulated because we have to address more stuff, and we divided it into macro categories, namely evasion, decryption, and loading. With regards to evasion, we implemented unhooking and anti-sandbox, and everything is implemented using direct system calls. After the evasion operations are completed, the payload is decrypted and we start the loading process, in which we perform different operations, which depends on the type of payloads it was provided as input. In particular, we implemented also a custom PE loader that supports both unmanaged and .NET binaries. With regards to shellcode, we implemented two different injection techniques. Since the debugger will inject the payload into itself, the difference between the two shellcode injection techniques is basically just the memory allocation scheme used. Let's talk about obfuscation now. The project uses the LLVM toolchain, and we decided to use Yansu LLVM to obfuscate the code. Yansu LLVM is a library that allows obfuscation at compile time. The output of the compilation is polymorphic, which means that signature-based detection won't be effective because the binary will be different at each compilation. The obfuscation is implemented into LLVM passes that manipulates the LLVM bytecode applying the obfuscation algorithms. We can apply passes to insert garbage code or to add false branches, for example, and the complete list of the passes can be found in the repository. And in this slide, we just wanted to show an example of the IDA output for a binary packed with PEzoNG, and as you can see, it's definitely not nice to watch.
Let's talk now about how system calls work in PEzoNG. As we have seen before, the system call module in PEzoNG is required in the evasion block of the unpacking process. This block is very important, and here we cannot afford to be detected by an antivirus since we are preparing the environment in order to execute the malicious payload safely. By calling a system call instead of using the corresponding Windows API, we bypass many detections, hooking in the first place. However, calling the NT function in NTDLL is not safe since they can be hooked too, so we must find a way to obtain the system call number and invoke it directly. For this reason, PEzoNG extensively uses the syswhispers2 technique in order to invoke system calls. This technique allows to dynamically retrieve the system call number by exploiting the fact that if we get the address of all the ZW functions and we order those functions by address in ascending order, we find that a lower memory address corresponds to a lower system call number. In particular, if we order the array containing the addresses of all the ZW functions, the number of a system call is then its position in that array. And this works also if the system call stubs are hooked, because we are only looking for their address and not the code. Finally, the name of the system call is hashed inside the packet executable in order to avoid the presence of suspicious strings, and those hashes are randomized during each packing process. The source code implementing this technique is available for 64-bit applications only, and since it contains assembly instructions, for 32-bit applications more work is required. So for 32-bit applications, the idea is the same, but the assembly stub must be different. We enhanced the code from the GitHub repository you can see here, which however only provides an assembly file with all the system calls, and we want only the system calls we use, not all of them, in order to have a lighter binary output. For this reason, now we provide the ability to generate the assembly stub like the syswhispers2 project for 64-bit, and we fixed two small bugs in this repository. Namely, in order to call the wow64 gate, we need to get the address from the TIB, and in the original repository, the stack allocation to store parameters has a small error. The number of the parameters is written in decimal instead of hex. And here, you can see the Python function which implements it. Given the name of a system call, it provides the assembly stub, exactly like the syswhispers2 project. The first evasion block executed by PEzoNG in the unpacking process is the AV Sandbox. Antivirus software usually execute unknown binaries in a sandbox process, where they can check whether the binary is malicious or not. This process only lasts a few seconds, and if the program doesn't do any malicious action, then it can continue its execution. Otherwise, it will be marked as malicious and the execution will be stopped immediately. We will see later that an antivirus cannot sandbox an application for a long time in order not to degrade the user experience, and we will exploit this in order to bypass it. The first sandbox bypass technique we are going to discuss about is the antivirus path hijacking. Antivirus software sometimes hijack the logical path of a process and change the branching condition in order to set it differently from what the program expects it to be, in order to check all the possible behaviors of a process. A McAfee patent was released some years ago about this concept. Since PEzoNG embeds the encrypted malicious payload, if we decrypt it with one step only, the antivirus will find the artifact in memory and is able to detect it. So the idea is to split the decryption process in two if statements, such that if the antivirus hijacks one of them, the payload will not be decrypted. And the only way that allows complete decryption of the payload is when neither the first nor the second if statements are hijacked. And here you can see the C code which implements this technique. If you look at it carefully, we have two variables, A and C, which are both equal to 1337. The two if statements inside the first cycle will be evaluated only once during the execution of that first cycle, and in particular in the same iteration, because the first and the last expression in both of the if statements are always true. In particular, A is always equal to 1337 and C is always different from 7331. The same for the second if statement. For what concerns the I variable, it will be equal to that big constant only once during the execution of the first cycle. So, if the antivirus hijacks any of these two if statements in any of the iterations of the first cycle, then the decryption will not be correct. Here in this slide, you can also see what we will talk about in the next slide, which is the offer you have to refuse. In particular, this is the first instruction of the first if statement, and we are going to discuss about it now. The offer you have to refuse technique is documented in a PDF you can download at the URL provided here. This technique exploits the fact that sandboxes have limited resources, as we said before. So an antivirus cannot scan a binary indefinitely because it would impact user experience. And to bypass this sandbox technique, we cannot simply call one of the sleep functions because the call can just be skipped by a sandbox. So we have to find a way to spend time until the sandbox releases our process. In particular, what we are going to do is do some computation that will force the CPU to work. At some point in time, the sandbox has to give up and stop the monitoring. What kind of computation we need to do? We need to do computations with memory dependencies so that the value of the variables cannot be guessed by the sandbox. The operations can be really simple, just like multiplying by 2 a variable. The only big requirement in this case is the memory dependency. We evaluated how much time do antivirus software execute new programs inside their sandbox, and we found that time matters. More or less after 12-13 seconds, the sandboxes give up. So the computation cannot be too fast, but at the same time it cannot be too long, otherwise our payload is never going to be decrypted and then executed. For this reason, the useless computation is executed in PEzoNG while measuring the time since the process started. When we reach the threshold of 12-13 seconds, the useless computation stops.
Okay, so time to talk about unhooking now. First of all, why unhooking? Because AVs and EDRs need to hook. Hooks are used to help monitoring the behavior of processes because Microsoft does not provide full kernel access to security products. Windows provides kernel callbacks for a number of events, but not all the interesting events have a corresponding kernel callback, and so security product must rely on user space hooking. One example is changing permission on a memory area. It can get caught by kernel callback, and so the AV need to hook anti-protect virtual memory, and sometimes they hook also higher level APIs, like virtual protect for example. Basically, if we remove the hooks, we will be able to execute some operations without notifying the security product, and this means that the AV will be partially blind. Let's have a quick overview to the hooking procedure. The basic idea is very simple. We want to hijack the execution of a function to execute some code that we control. And in this way, it is possible to detect when the function is called, and we can also evaluate if the function can be called or not, for example, basing on the passed parameters. To achieve this goal, we have to patch the function prolog, and in particular, we can patch the first instruction with a jump that will point to our code. However, this is not always straightforward, because there are some details to take into account, for example, instruction alignment. Moreover, it is responsibility of the hooking function to correctly restore the original execution path, and so the hooking functions have to take care of those details to avoid crashing the monitored process. So, let's use an example to analyze deeper how hooking works. For this example, we will analyze an anti-close hooked by detours. First of all, a jump is set at the first instruction. The jump points to a stub that is used to redirect the execution to the AV DLL. The AV DLL code will be executed, and the AV will evaluate if the call is allowed or not. If the call is allowed, the AV DLL code will jump to another stub that actually contains the original prolog instruction, and this final stub will eventually jump back to the hooked function at an offset that depends on how many instructions have been overwritten. It should be noted that this is just an example, and in real world, there are more than one way to jump back to the original function. In particular, we have identified three ways: absolute jumps, relative jumps, and double push technique. So, we will find one of those three techniques in the stub that contains the original function prolog. Okay, now that we know the basics of hooking, we can go back to the evil stuff. In PEzoNG, we implemented two unhooking techniques: Shellcode and Whisper to Shout. Shellcode is a well-known technique, and Whisper to Shout, on the other hand, is a novel technique that improves OPSEC. Let's start from Shellcode. This technique reads from disk the original non-hooked DLL and overwrites the text section to remove the hooks. To map the clean DLL in memory, we have to call anti-create-file, anti-create-section, and anti-map-view-section. After that, we have to change the protection of the test section by calling anti-protect virtual memory, so we can overwrite the hooked DLL with the clean one. Then, we overwrite the instructions using, for example, memcopy, and we finally unmap the section by calling anti-unmap-view-section. This technique, however, has some pitfalls that might trigger detection, and in particular, the DLL will be mapped twice in memory. After that, we have to call some OS functions to map or unmap the images, and since the EDRs may use kernel callbacks to detect image loading events, loading a DLL twice, for example anti-DLL, might look very suspicious. Finally, some AVs may check hook integrity. So, if we overwrite the hooked DLL with the clean one, the hooks will be set again after a short time, and so our unhooking techniques will be not effective at all. Now let's analyze how Whisper to Shout works. This technique needs just two system calls: anti-query virtual memory and anti-protect virtual memory. We want to use system calls to avoid user space hooks, since those functions might be hooked. And the basic idea is work the process address space in a smart way, find the original prolog, and then patch the memory to skip the hook. The problem is, how do we find the prolog? So, when we started to work on this idea, we looked at Microsoft detours. We noticed that they use virtual alloc to allocate the memory for the stubs. And this choice makes sense, cause virtual alloc is the best candidate for allocating executable memory at runtime. Thanks to memory metadata, we can identify memory allocated with virtual alloc, and this information will be useful to exploit Whisper to Shout. Let's now open a dummy program in the debugger to see what happens when a function is hooked. In particular, we are going to analyze RDR load DLL hooked by AVG, and we are going to use X64 for debugger. This screenshot shows the instructions at the symbol address when the function is hooked, and as you can see, there is a jump that points to an address not resolved by the debugger. If we follow the jump in the debugger, we find another jump, directed to a memory area located in ASW hook. This sounds very interesting, and indeed it is, because ASWHook.dll is actually the AV DLL that implements the checks for the hooked functions. And by following the jump, we arrive in the AV DLL. In this function, we can see that there is a call to another location in memory, and again, the debugger just uses the address to reference it. If we follow that call, we will arrive in a memory area that contains the original function prologue, and this sounds like a win. Moreover, we can see that after the prologue instructions, there is a jump to an address inside anti-DLL, and this is actually the remaining part of the function. So, we found the stub and the prologue, and we are ready to exploit Whisper to Shout. Let's summarize. Here is the memory layout for AVG. The private memory area contains all the stubs we need. We can find the stubs by following the pointers starting from the first jump, and we can understand that we found the right stub by cross-referencing those informations. In particular, if we find a jump to anti-DLL at an address near the target function, it means that we found the original prologue. As already mentioned, it should be noted that there are three ways to come back to the original function, but the concepts are exactly the same. The only difference is in the patterns we will use to identify the redirection to the hooked function. Now let's summarize what we have. The hooking stub is stored in a private memory area, and it can be retrieved by following the jump placed at the symbol address. The original prologue is stored in a private memory area as well, and it contains a jump to an address that is near to the address of the function we want to unhook. So, to retrieve the stubs, we have to scan the private memory areas in the process address space searching for a pattern. Namely, we have to find the jump back to the hooked function, and, moreover, the research can be done in a smart way by following the pointers, so that we won't actually need to scan all the private memory areas. So, let's see the idea behind Whisper to Shout using a scheme. To retrieve the stub containing the prologue, we have to work the pointers. So, once we have identified the original function prologue, we could just copy it, overriding the jump set by AV to hook. However, some security products monitor their hooks, and they periodically check if the hooks are in place. So, how we solve this issue? To solve this issue, we thought to overwrite the hooking stub instead of the original function, so that the API function will actually be hooked, but since we hijacked the hook, the AV code will never be called.
After the evasion and decryption processes, the payload is loaded into memory in order to be executed. PEzoNG supports the loading of a shellcode, a PE, which is a standard Windows executable, or a .Net executable. In any case, we support both 32-bit and 64-bit applications. Let's start with the shellcode loading. In PEzoNG, we implemented the classic pattern, which is allocate memory to host the payload, copy the payload, and finally execute the payload. We will deal with memory allocation later on with the slides, because it is very easy to allocate memory such that an antivirus or an EDR is able to identify it and proceed with more inspection on your process. And we don't want this, since it would break everything we did to reach this point of execution. We are just one step before executing the real payload, so we cannot afford to be detected. After copying the payload, we step through the execution, which will also be discussed with more details later on, but for now, what we can say is that we just jump to the first instruction of the payload. No thread creation, no injection, only a simple jump, and we will see later on why. For PEs, the standard Windows executables, we implemented a custom loader, which just replicates what the Windows loader does while loading a PE from disk, or while you double-click an executable file from the graphic interface, for example. Our loader has support for many PE features, like relocations, imports, exception handlers, but only for 64-bit programs, PE resources, and this involves tampering with the PEB of the current process, TLS callbacks, and parameters handling. If the embedded payload is a PE which requires command line arguments, you just need to call the packet executable with the same arguments. Nothing more is required. We wanted to make sure that the usage experience is as simple as possible, so a packet PE should be used like the original PE. Without entering into the details, the high-level steps of loading a PE are the following. We allocate memory to host the PE, and as we said before, we will give more details later on about memory allocation. Then we copy the PE sections, and before jumping to the entry point of the application, we need to execute some operations in order to be able to successfully execute the payload, like for example, resolving the imports of the applications or fixing the relocation table. An executable file usually imports functions from other DLLs. These DLLs must be loaded into the memory space of the process, otherwise the application is not able to find them. Finally, PEzoNG is also able to load Dotnet executable. The loader is the same process, so an unmanaged process, which loads an instance of the CLR, so the Common Language Runtime, compatible with the requirements of the PE. But just before doing that, we want to make sure that ETW and AMSI are patched, and we can do that from user space without any troubles. So now, for the Dotnet case, the environment is safe in order to execute the embedded payload. So we load the Dotnet assembly in memory, and we just call the main function. Okay, let's now deal with the memory allocation. As a reminder, what we say now is exploited both when we load the shellcode and when we load the PE. This module is very crucial, firstly because when malwares allocate memory, they can leave known artifacts in RAM, thus making both a forensic analysis and a runtime analysis easier. Also, antivirus and EDRs monitor patterns of memory allocation which lead to code execution. So, what we would like to obtain is the allocation of some memory that can also be executed, but not detected. Windows already has something like this embedded into it, which is the loading of a DLL. For this reason, we tried to mimic this behavior and obtain a memory area which is almost identical to what Windows would allocate for a legit DLL. The standard way to allocate memory is with the virtualalloc API, which in turn calls the virtualalloc API, which in turn at some stage calls the ntallocate virtual memory syscall. The good point is that this is a very simple to use syscall, and it often succeeds. Moreover, in PEzoNG we now have a way to execute system calls safely, so it's very simple to use this syscall to allocate memory. However, this system call has been used widely by malwares, and it leaves known artifacts in memory, so we must find a different way. In particular, we can see in the highlighted red box that the type of pages allocated with the virtual alloc API are of type memcommit. So, if someone wants to find suspicious pages with shellcode, in this case they are talking about Dotnet, which is a different project, but they are allocating memory with virtual alloc, so the concept is the same. And if you want to find suspicious pages of memory allocated with virtual alloc, the simple way is just to check the state field of the memory basic information returned by virtual query X, and this field should be memcommit. In fact, you can see here an example of the Mimikatz process packed with PEzoNG, when we allocate memory with NT-allocate virtual memory. As you can see here, we have two memory regions of type private and commit. And if you look at it from the defensive point of view, the most strange thing in these memory regions is that the permissions are read, write, and execute. And this is a very common thing in malwares, as they need memory which is both writable and executable. So, we decided to opt for a different approach. In particular, we implemented the module overloading technique, as briefly explained in a tweet by the Wower. The concept is very similar to the classic DLL hollowing technique, since we are going to load an existing DLL into the process address space and overwrite its content. However, with the module overloading approach, we don't need to have write permissions over the DLL file. The steps for the module overloading technique are the following. We first need to find a sacrificial DLL which is not loaded into the process yet. This is crucial. The DLL must not be already loaded into the process address space. And also, the size of this DLL must be greater or equal to the size requested for the allocation. So for example, if we want to allocate 1 megabyte of memory, we must find a DLL whose size, when after it will be loaded into the memory, is greater than 1 megabyte, greater or equal. Then we open the sacrificial DLL with the read-only flag, and we map it with the two syscalls, the nt-create-section syscall and the nt-map-view-of-section syscall. This time we use the read and write permissions, since we are going to overwrite the content of this memory, so we need also the write permission. If you notice, we called the nt-create-section system call with the sec image flag. So, since we are mapping, we are creating a memory region with this flag, and then we map this region into memory, we will see that it appears as a legit DLL loaded by Windows. Finally, the last step is just to return the pointer to the mapped section. Here we can see the difference between memory allocated with NT-allocate virtual memory and memory allocated with module overloading. In the first case, the memory is of type private commit, so easily detectable, while in the second case, the memory is of type image commit. Moreover, on the right, we can see that the memory is associated with a DLL on disk. And in this case, the DLL is aadtb.dll, which is a Windows DLL. And here, we can compare a memory region allocated by Windows to host a DLL with the memory region allocated by PEzoNG to host the malicious payload with the module overloading technique. We can see that they are really similar, actually identical. So, from this point of view, we managed to allocate memory that is almost indistinguishable from the memory allocated by Windows. However, there are some caveats which we'll discuss now. There are three main issues with the module overloading techniques. The first issue is that the sacrificial DLL is not added to the PEB list of loaded modules. So in a Windows process, the PEB contains a list of all the loaded modules of the process, and we mapped a new DLL without adding it to this list. The solution here is simple. We just need to add the sacrificial DLL to the list of loaded modules by adding a new entry to this list, and this list is contained inside the process environment block. The second issue is that the section permissions in the sacrificial DLL headers may be different from the actual section permissions in RAM, since of course the header of the DLL is going to be different from the header of the PE we are going to load in memory. So the solution here is to get a sacrificial DLL with the requirement that not only the size should be greater or equal to the requested size, but the size of each section of the sacrificial DLL must be greater or equal to the size of the corresponding section of the PE we want to load. This is very difficult to solve because we need to be consistent with every section, but we can do it. It's solvable. The third issue instead is that the content of the sacrificial DLL in RAM is different from the content of the sacrificial DLL on disk. Unfortunately, there is no way to address this issue, since of course we are going to overwrite the memory region allocated with the malicious payload. So this is the only artifact left by the module overloading technique.
Okay, we are almost at the end of this journey. We finally arrived to execution. After all the environment has been loaded and organized, if we load the PE, we have to set some values in the PEB. Namely, we have to set up base address, entry point and size of image. Then, we just have to jump to the entry point by calling the code with a simple function call. We decided to load the payload in this way so that it will run in the same thread and we don't need to call any Windows API or system call. In this way, since we are just calling a function, the OS is not involved in the operation, and the AV cannot see that we are running the payload because it won't get notified by the kernel. On the other hand, thread creation could easily get caught by the kernel callbacks, and so it could trigger further analysis that we want to avoid. And finally, it's demo time. We prepared videos where we are going to run some malwares on a fully updated Windows 10 20H2 protected by Windows Defender. We activated all Windows Defender protection except the automatic simple submission, and we prepared 3 proof of concepts to show the 3 major cases, namely Shellcode, Unmanaged PE, and Dotnet PE. Let's start with the Shellcode. In this video, we packed a stageless Cobalt Strike Shellcode. After generating and packing the shellcode, we run it in the Windows box, and we have to wait around 13 seconds due to Sandbox evasion. Please note that the video was speeded up to save time in the presentation, and so the delay is smaller in the video. In the next video, we show an unmanaged PE. We packed Mimikatz and we run it in the same Windows 10 20H2 environment used before. The final proof of concept shows a .NET binary. We choose a SharpHound for this demo. Finally, this screenshot shows the packed Cobalt Strike Shellcode showed in the video, scanned in antiscan.me. As you can see, we got a detection rate of 0/26. Thanks for the attention. We hope you had a good time watching this talk. Cheers!